So welcome, Dr. Starkey.
Thank you.
I know that we want to get to the point of talking about how these things are going to kill all of us, and we're all doomed. But before we do that, before we get started about that, we should talk a little about what these things are that are going to kill us all. Your book, of course, is a nonfiction book, but I couldn't help thinking while reading it that if it were a novel, the main characters in it would be comets and asteroids.
Yep.
So maybe we should start there. Talk about a little bit about what comets and asteroids are and how they are different from each other.
Sure. Okay. So I guess there's a lot of misunderstanding now about what the difference is between comets and asteroids. So classically, we had this idea that comets formed in the very cold outer reaches of the solar system. So when our sun first formed, it was surrounded by this cloud of gas and dust and ice. And way out in the outer reaches of the solar system, way past where any of the planets are today, we formed the comets. And they're literally just like describe it as like a scoop of this cloud. You basically just take this gas and dust and ice and kind of bind it together a little bit, but they're not very well held together. They're not very well consolidated. So they're almost like a snowball, essentially, with a lot of dust in. But why they're so important is that they're exceptionally old. So they're as old as the sun, 4.6 billion years old, which means they can tell us a lot about where we came from, where everything in our solar system came from.
Right, they're sort of primitive objects.
Exactly. Whereas the asteroids, on the other hand, they're also very old, with saying probably nearly 4.6, if not just about 4.5 billion years old. And we can think of those as kind of the leftover building rubble from making the planets. So they formed in the inner solar system, much closer to the sun, just as the rocky planets did, like Earth and Mercury and Venus and Mars. And it was just those bits and pieces of planet that didn't get made into a planet. They just got left out. And then they collected in the asteroid belt, which is now between Mars and Jupiter. So the asteroids are really important because they preserve this history of planet building, which is really hard to look at, because if we just take Earth, we've had all sorts of evolution on Earth since it formed, and we have plate tectonics, as most people know. So especially living in LA, you probably know too well, there was an earthquake last night actually, that our plates are moving and we create earthquakes and volcanoes. And this changes the surface of our planet. So if we want to go back to the beginning of Earth, we want to see what it was made from and how it started out and how life got here and how our water got here. It's really hard to do. It's really hard to pick apart that history. So asteroids are really important in that sense. They can kind of allow us to glimpse back at that time, because they didn't really evolve since they formed. Not a whole lot anyway. They sort of preserve those conditions. So. Right. That's the classic view. And I think we're going to come on to in a bit kind of how that view is maybe not so accurate now. It's not wholly wrong, but we've kind of updated our view about these objects. So, right. But we should remember that that's the classical distinction.
And I love that image of the asteroids as kind of the leftover Legos from the solar system. You snapped a whole bunch of things together into planets, and these are the ones that are kind of scattered on the floor.
Yep, that's really good.
And so because these might come into the picture as well, can we talk a little about what meteors and meteorites and meteoroids are?
Yeah, so there's a lot of confusion about that. So a meteorite is literally just a piece of rock from space on another planet. So on Earth, we can go and collect meteorites sitting on the ground, and it could be a piece of a planet, it could be a piece of a comet or an asteroid. And what happens is that collisions happen in space, and they've happened for millennia. And little pieces of rocks will get knocked off planets if an asteroid collides with them. And some of this asteroid might end up just floating about in space, but little pieces of it. So it's a meteoroid in space, and then when it comes through the atmosphere, it becomes a meteor. So we had the meteor shower recently that you can see little pieces coming through. Often that's dust. When we get a big fireball, these beautiful scenes that we get, that's a larger piece of rock coming through. If that rock makes it to the surface, if it doesn't explode in the atmosphere and completely disintegrate, a piece of rock on the surface is the meteorite. So the great thing about them is that we can collect them. Sometimes we can actually see them fall. If you see a fireball, you can sometimes trace it and then find that fresh rock, literally just straight from space, and you can sample it. Or we get older falls where, these are called finds, where they fell a while ago, it could be millions of years ago, and we can then go and sample them. And it's great because it means that we can get samples from space, because we don't actually go into space very often. We go into space a bit, and when we do, we often don't collect samples, because if we want to go out and collect samples in space, it's almost like two missions. You want to, this is why we haven't sampled Mars, and people find that quite surprising when I say we don't have any samples from Mars. We've been there a whole lot. There's loads of instruments on Mars, but we haven't brought back any rocks from there.
Because not on purpose.
Yeah.
Right.
So we will be doing it in the future,
Right.
but at the moment the only rocks we have from Mars are meteorites. So
Exactly.
that's the only way we can sample them. They're free samples, which is great,
Right.
but we don't know exactly where they came from. So if we send a mission there, we can sample exactly in a particular basin that we're interested in, and then we can bring that back. But that's basically a second mission to relaunch off another planet or an asteroid or a comet. It's really complicated. So that's why we haven't done it very often. Obviously, we have a lot of samples from the moon, thank goodness. So that's,
Right.
yeah, we've done it a bit, but we need to do it more. But we have meteorites in the meantime, which can really help us out.
Right. Okay, so the asteroids all live, well, not all live, but are mainly collected in the asteroid belt, which is this region between the orbits of Mars and Jupiter.
Yep.
And the asteroid belt, I learned from your book, isn't really all one thing, right? There's like an inner and an outer belt, and there's a distinction between those two regions. You want to talk about
Yeah,
that a little bit?
so when we studied asteroids and asteroid belt, we kind of initially thought they were all going to be the same, just these kind of rocky objects that look a bit like, failed planets, and these small, and they're all very small. There are a couple of large objects there, but actually when we look in detail from the inner belt, which is going to be the bit that's closer to Mars, sure enough, these things do look like asteroids. In fact, some of them are made completely of metal. So if you take the core of Earth, that is made of metal. We all probably are aware of that, but actually we can sample a sort of core from a planet if we sample some of these asteroids. And there's a NASA mission actually going in the 2020s called Psyche, and it's going to look at one of these objects. So we can sample those, and they're very much like we consider the classical asteroids. But as we move out to the outer belt on the kind of Jupiter side, what we find is that they change and they actually become icy, some of these objects, and they have a lot of carbonaceous materials. So what I'm saying here is that we've got organic matter. Now, that's not uncommon. We have organic matter in most of the asteroids, apart from the ones that are really made of just metal. This isn't life. People get very excited when we say organic matter.
Right.
It's not life. It's literally just carbon-hydrogen bonding and some oxygen, and it's organic matter that is potentially the precursor for life. So it's really exciting these objects contain a lot of organic matter, because we still don't understand how life got to Earth. We're obviously the only planet we know of that contains life. We don't know how it got here. And it's kind of it's ridiculous, right? I always find it quite funny that we still don't know how we are here. And we're like these very intelligent beings that can do all sorts of amazing things, but how we got here is a mystery. So we want to study these objects to try and understand if they could have delivered life. So these asteroids on the outer belt, they also contain ice. So they look very much like the comets that I described at the beginning. And actually, this is where this kind of distinction between the two objects breaks down a little bit, because these actually might be comets. When they formed, the idea is that some of them really could have formed in the outer solar system. And then there was a huge reorganization of the solar system after the large planets formed. And some of these comets kind of got thrown into the inner solar system and got trapped in the asteroid belt. So we actually find that they're kind of comets, but they are asteroids. So it's kind of confusing in that respect, but the same happened the other way. Some of the asteroids that formed near the sun got ejected out of the solar system. Some of them probably disappeared from our solar system completely, and others ended up in one of the homes of where the comets live now. So there's probably almost certainly some objects in what we call the Kuiper belt, where Pluto lives, which are probably asteroidal in origin, but now they're sitting somewhere very cold. So there is this is where kind of the overlap starts to happen, because the solar system's kind of crazy.
And I loved that image from your book of Jupiter sort of throwing a tantrum and rampaging around the solar system and kind of throwing stuff all over the place and kind of mixing it all up, so it's not arranged, in this kind of neat, tidy little categories that we thought at first.
I think that's the thing. We had this beautiful view, because the solar system is very hard to understand. Obviously, we need to visit it to understand it, and we haven't been to, we've been to a lot of it, but we still don't know how all the planets formed. And Jupiter is enormous. It really controls our solar system, and its gravity, if it decides to move around, which it did in the past, can just really cause havoc throughout. It can just knock planets around, and particularly smaller objects like asteroids. So that period of our solar system history is very, very crazy. So.
Yeah, you talked about it swapping the orbits of Uranus and Neptune. So Neptune is further out currently, and Uranus is closer in, but they were the other way around.
Exactly. So this is what we think.
It's really reconfigured stuff.
Yeah, and these are massive planets, and they have huge gravity. So it's kind of crazy to think, and obviously it's not going to happen now, but what we can do now is look out to other solar systems around other planetary systems around other stars, and we can kind of look at what is happening now. So I love that this is not my field, but this is astronomy, and it's absolutely fascinating that we can look out and we can kind of see our solar system as it was billions of years ago, because we can look at other stars and see actually planets forming at this very time, what kind of was happening here. So this is another way we can try and figure out what happened 4.6 billion years ago and afterwards. So it's fascinating.
Right on. So in much the same way that there's these kind of two regions of the asteroid belt, there's kind of two regions of where the comets live as well.
Yeah.
You talked about the Kuiper belt, which is the near region, and there's also the Oort cloud, which is a farther region. You want to talk about the distinction between those two regions as well?
So
and kind of how far away they are?
It's kind of crazy. So distances in space are always, I think everyone just goes, oh yeah, it's really far. It's like really far to Jupiter, and it's really far to Pluto. We know we went to Pluto with the New Horizons mission recently, and it's still going through the Kuiper belt. So a couple years later, I think it was 2015, it met Pluto, and it's still going through the Kuiper belt. So it is 25 times wider than the asteroid belt, and the asteroid belt is already fairly large.
Right.
And it's just, in terms of distances, it's not that far. So it's just past Neptune, Uranus. It's kind of just on the edge of the solar system. But these objects that are there, they're icy, they're dusty, they're kind of mostly fairly small, and we can see most of them. So we kind of know roughly what is there. But they're sort of bound to our sun by the gravity. They're not too far that they're not kind of bound to our solar system. But once you get to the edge of the Kuiper belt, it sort of becomes no man's land. We have a region called the scattered disk, which is just some random objects, which are probably mostly cometary, and they're kind of on crazy orbits a little bit, and we don't understand them a whole lot, but we can't see all of them. But they're kind of, we know that they're there. But then we get to this theoretical phase of the solar system, which is the Oort cloud. And I was fascinated to learn when I did a few years ago that the Oort cloud is not proven.
Right, we've never seen it. It's so far away.
And we always talk about Oort cloud comets, and we have what we call long period comets, which are these comets that come into the inner solar system and orbit the sun, and they have to have orbits of more than 200 years. So. The way we know the Oort cloud is there, partly because we have to balance out the mass of the solar system somehow. So we kind of, guess there had to be something out there. But then we get these comets coming in at really random angles into the. So basically, I should probably just sidestep a little bit. The solar system, as most people know, all the planets are on the same plane. And so is the Kuiper belt. So we're sort of all going around the sun nicely. Pluto's doing something slightly different. And then we move out to the Oort cloud. And this is literally a cloud around the whole sun. So what happens is when one of these comets decides to come into the inner solar system, they can come in from all random angles. They're not going to be coming along that plane. So that's how we sort of know this cloud is there, because these little visitors from the outer solar system come in and we can spot them. But we can't directly see them if they're there, because they're just too far away. These objects are tiny and they're too far away. So this is partly why until New Horizons got to Pluto, we didn't really know much about it. We just could not really see it in any detail. So I'm really excited to see the next object it's going to in the Kuiper belt, and then the Oort cloud. We're never going to get there in anyone's lifetime. It's just the spaceships will continue going, but we are not going to. No, they will have run out of battery by then anyway. So
yeah. So doing the math on the numbers from your book, I got that light leaves the sun, it gets to the near edge of the Kuiper belt in 4 hours. Okay, so that's the Kuiper belt. It gets to the near edge of the Oort cloud in something like 9.5 months.
Okay,
so that's the magnitude of the difference that we're talking about.
Yep, and then the Oort cloud, it would take another 2 years to cross,
right,
probably, or something like that.
Yeah, so exactly right. It's like from 1 to 3 light years in distance. Yeah.
So when you're talking just spacecraft speeds, this is going to take tens of thousands of years, I'm guessing.
It's something like 40,000 years or something along those lines.
So it's very far. So I think,
we don't have batteries that will last that long.
These objects are barely bound to our sun. They are actually influenced often by, in the galaxy, the passing of other stars. They can be knocked out of their orbit by literally other stars nearby, because they're almost closer to other solar systems or stars than our own one.
That was the thing I was fascinated, just a little factoid I was fascinated by from your book, that the outer edge of the Oort cloud, which is around our sun, is actually closer to the next star than it is to our sun.
But they are literally within our solar system. So it's kind of where you define the edge of the solar system, and there are different definitions for where it is when you enter interstellar space, which is the bit in between the stars. And so, the Voyager missions, which set off in the 1970s, they are now in interstellar space, but that just means they are past the Kuiper belt, basically.
As long as we're talking about awesome little facts from your book, the asteroid. This is a thing that kind of blew my mind. The asteroid belt. All the asteroids from the asteroid belt put together would have less mass than Earth's moon.
Yeah.
Yeah, which is very different from your picture of it. As you think of the Millennium Falcon swooping through the asteroid belt, and the asteroids are all kind of like huge and close together. And yeah, but it's really kind of like scattered.
They're quite scattered
out,
and that's a good thing. Otherwise, they would collide more often, and we would have more issues in the inner solar system with potentially being hit by one. So actually, it's a good thing that they're nicely far apart, so you can get through quite easily. You can find a good route.
Well, that's a nice little transition for us. So now that we have a handle on kind of what all the players are, the comets and asteroids in the solar system, and the meteors, of course, once they get here, let's talk about how they're going to kill us all.
Great.
So one of the things that you talked about in the book is you kind of point out that comets and asteroids giveth, but they also taketh away. That they might have brought life to Earth, but they also wiped out the dinosaurs and could do the same to us. I'm a little hesitant to ascribe properties like good and evil to inanimate objects like that. Maybe we should talk about them in helpful or scary. But how do you think about them? Do you think that they're things that should be revered or feared, or?
So, I mean, it's probably no surprise as somebody who's researched these objects for quite a while that I revere them.
Fair
because
enough.
One of the things about it is, yes, they do have the potential to collide with us. And we think we're safe for about 100 years. So probably all of us, unless you know how to live a lot longer than 100 years, then you're going to be okay. But the thing is, like, are our descendants going to be okay? And the more we can learn about these objects now, the better prepared we are to do something about one of them hitting us. So if we don't understand our enemy, then we don't know how to fight it, basically.
Sure.
So
right.
I love these objects because they can tell us a lot about where we came from, about our past, and how everything started in the solar system. But yeah, they do really have the potential to cause havoc. A large asteroid could hit us. Past that 100 years, I mean, there's a chance one could hit us within 100 years, but it's very unlikely. Past that, we at the moment don't know. It's a kind of a continuously updated list of potentially hazardous asteroids and comets, which astronomers are studying, and they need to understand better how they move on their orbits and what their next orbit of the sun is going to do, and if they're going to be altered by passing Jupiter in the future or something. So we need to understand exactly what they're doing, how they're spinning, and then we need to know what they're made of, because if we don't know what they're made of, well, some ideas, like Armageddon, if you've seen the Hollywood movie, they actually go and detonate some explosive inside the asteroid to blow it up. Well, it depends what you're dealing with. If this asteroid is made of pure metal, that might not work. You might not even be able to drill into the thing to put some explosive with inside it. But if we're talking about a comet, well, maybe if it's coming towards Earth, it might just explode on atmospheric entry anyway. So it's kind of like, okay, we need to know what we're dealing with if we want to go and deflect or destroy one before it gets here.
Right. And you talk about this some in the book, that even blowing up the asteroid might not be good, because now you have a whole bunch of asteroids that are going to kill you instead of one big asteroid that's going to kill you.
And I think one of the things is, like, the more advanced notice we get, the better. So if we can see that an object is heading for us and it's large, say a kilometer or so, and it's 10 years out, then we have time to launch a mission. This is why we need to do a bit of work in advance, because of course it's not that easy to launch a mission just straight the next day. So we need a few years to figure out how to launch the mission there. It'd be great if we had one ready to go for any of these objects, which is what we're currently working on in Planetary Defense. It's a big topic at the moment in research, and governments are actually interested in this, which is great, because we need them to support the research community. Launch mission, basically, the longer you have, the better. If you want to deflect something and it's way off, it's going to be a smaller nudge to deflect it. If you just want to push it out of the way, then if it's right next to Earth already, you're going to have to deflect it a long way for it to miss. Ideally, we'd want to deflect them. We just want to put it on a different course so it misses our planet. We don't care if it hits another planet, but we want to protect our own planet. We could, if we're stuck and we don't have much notice, we could explode it in some way if we can find a way. Of course, you might need to use nuclear weapons, which is not going to be fun if you're going to get the rain of this nuclear weapon falling down on the planet. But
and it's possibly in violation of treaties, although that would probably be forgiven if you were saving the entire planet.
I think if we, so I think nuclear weapons aren't allowed to be used in space as like in a bad way. So I think if we were saving our planet, then we'd probably let it go. And maybe some nuclear fallout wouldn't be as bad as just being hit by an asteroid. So we might allow it. But it sounds like science fiction, and it is science fiction, but it's also now turning into reality. These are really kind of what we're thinking of. There's other crazier ideas that we don't have to explode these things. There's other other ideas like we can spray paint one side of this object. So generally these objects are very dark. And as they go via the sun, they obviously get heated up. Now, if you can change one side of that asteroid, if you could spray paint it white or metallic, it's going to heat up differently as it goes near to the sun, and it will start spinning differently. And if it spins differently, it'll change its orbit gradually. So these are very gentle techniques. It sounds a bit mad trying to spray paint in space, but this is literally one of the things we could do, or cover it with something to kind of change how it reacts to the sun's heat. So.
You know, I never saw the movie Armageddon, but I gather what it's about is they sent. I haven't seen it. But I gather what it's about is they sent like basically miners to space.
They sent Ben Affleck and Bruce Willis up there, because they were oil miners. Yeah, they were drillers. So.
But so it had never occurred to me. Like I kind of get that, but it had never occurred to me that maybe what you want to send is taggers that could spray paint the side of the app, right?
Yeah,
like maybe they would do it. They would put a nice mural on the side that would look pretty as it passed us by safely. Yeah,
I mean, in reality,
we're going to work on that. That's your next book, right?
I think I should do that. That could be the novel.
Right? Yeah. There you go, the novelization of the.
But yeah, I mean. Of course, we're not actually going to send people up. If in reality, what's going to happen is that we use robots. And in space, of course, all the time we use robots, just because they're more expendable. We don't really care if we kill the robots. We care because they cost a lot, and a lot of people's careers gone into making them, but
some
we're not
of us really
people.
fall in love with
them. Don't we all? But it's not humans. So there's big issues of sending humans into space. And if we're going to send them to land on an asteroid, well, asteroids don't have an awful lot of gravity because they're small objects. So they're going to have to be tethered on. I can't remember what they did in Armageddon. If they were, I think they were just roaming about freely. They would probably have floated off into space, you know. So it's not easy to send humans to these objects. I'm sure it will happen in the future, you know, way into the future. But for now, it will be robots, which again is not easy because, as you know, trying to run a robot from Earth and millions of miles away has its issues. Communication times are tricky because it takes a long time to communicate.
Can't joystick it.
Things go wrong. Like I ran a lab instrument for many years and I could be in there tinkering with it, and if something went wrong, I could change things. But if that instrument is way off on an asteroid, there's nothing you can do. If it breaks, there's not really an awful lot you can do. So yeah, there's lots of issues.
So, but we have actually sent space missions to these objects, to comets and asteroids before, and it was. I would say it was pretty evident from reading your book that you're a big fan of both the Stardust and Rosetta missions.
I am, yeah. They got a chapter each.
And speaking of landing something on one of those objects, Rosetta actually did that.
Yeah.
You want to tell us a little bit about those missions and what they accomplished?
I mean, the NASA Stardust mission was like, it had happened and it had brought its samples back, like as I was starting my career in this area of science. So the NASA Stardust was really groundbreaking. It was actually quite a cheap mission, and it flew to Comet Belt 2. And it wanted to bring a sample back, but it didn't have enough money to land on this object and come back from it. So they flew through the tail of the comet. So I've mentioned that comets have a lot of ice and dust in them. And as they go via the sun, this material gets heated up. So sure enough, the ice streams off the comet and takes dust with it. And that's what produces the tail. When you get the famous comets that you see all the beautiful images of, that tail of material is literally the gas and dust coming off of that comet. And so what they did was just flew through the tail of this comet and literally just got impacting particles on this collector. And that was their comet samples. And they closed up their little collector and jettisoned it back to Earth. And the rest of the spacecraft carried on. And we had those samples back in 2006. And they were our first real samples of a comet, because it's hard to know if we've got any meteorites of comets because, as I said earlier, they probably explode as they enter the atmosphere. So it's hard to know we've definitely got one on Earth. So this was a real groundbreaking mission, and then it also really turned the books on how we thought comets formed. And what it showed us was that actually we know it's a comet, it behaves like a comet, we know its orbit, that it comes from, from the Kuiper Belt, and then what we find is that actually it doesn't look like a comet. When we look at the rocks within it, they look like an asteroid. So it doesn't sound very exciting, but you're like, hold on a minute, this thing formed way out in the outer solar system, yet it's got components within it that look exactly like the planets, that look exactly like the building blocks of the planets that form very close to the sun. So how do we get ice and hot material contained within one object? So this was why everything got blown apart at this stage, and the scientists, and they're still working on it. We still are trying to understand how we get hot material from the inner solar system out to the comet-forming region to form a comet that then is covered in ice and dust and all the normal stuff that we expect it to contain. And there's lots of different theories, but that is still an ongoing area that we need to understand. So we know that the story is not as simple as it could be, as we'd like it to be, as the textbooks would have us believe.
Before we move on to Rosetta, Stardust also brought us back, in addition to bringing us back the first sample from a comet, brought us back samples of interstellar particles, right?
It did, yeah.
Turned the detector around, did it the other way, and collected a few of those as well.
So yeah, basically we have particles from interstellar space, which is the space around all the stars in the solar system, and these particles are traveling exceptionally fast, and we haven't really been able to sample them before. But so this it was called like a tennis racket style collector. It kind of just came up out of the spacecraft. One side collected comet particles, and then the back side collected interstellar particles. And they're tiny. They're so tiny that we can't, the comet particles are small. I'm saying probably a maximum of the width of a human hair would be the largest particles we collected, if that. The interstellar particles are 10 times smaller than that. So they're very hard to see on the collector, and they're very hard to analyze, but there was a whole instrument built somewhere in LA, or somewhere in California, I can't remember which university it's at, but they basically made a whole instrument to measure these particles, because we can sample then our galaxy, because we have no other way. We haven't been able to go out to our galaxy, but these particles come to us. So we can actually start to understand what our galaxy looks like and what it's made of, which is fascinating. So yeah, it was, it just did so much, that mission. It was fascinating.
Right.
So.
There were some other really interesting things in there. You go into a lot of detail about exactly how they were able to get some of the samples out and so on. But and we might want to come back to that. But I did want to also give you a chance to talk about Rosetta as well, because that was fascinating. Such a great mission.
So I was just really well placed. I'm really lucky to be where I was working when the Rosetta mission was ongoing. Now I have to say I wasn't in it from the beginning, because it took 20 years to plan this mission. In fact, I think when it was originally being planned, I was probably still in school, primary kind of school, very early. And then it took a long time to build the mission, and then it took 10 years for it to actually, from launch, to get to its comet. So it had this massive journey in the solar system to catch up with this comet. So this comet called 67P Churyumov-Gerasimenko.
Yeah, I can't do that. I like everybody else, I just say Cherry Jerry.
Oh yeah, you can say CG or 67P. Yeah, it's a long name. But it was traveling into the inner solar system, and the idea was that they launched and had to do some gravitational slingshots of different planets to catch up with it, get enough speed, because you can't just launch and go directly into a comet. That's literally not how it works. So we have to just catch up with it. So it got onto an orbit eventually to catch up with the comet, came up on it from behind, and then entered into orbit around this thing. Now, we've never done this before. So, Stardust just flew through the tail, but Rosetta was just amazing. It got to the comet, and it basically had to do it couldn't get into orbit around it because this object's small. It wasn't a real orbit, but
so
it
there's
was
not enough gravity
powered
to keep the
flight
spacecraft
around it. So these people doing this engineering and all this science for this mission, I just am amazed by how they did this. But they didn't even know what this object looked like. Before we got there, we had no idea of its shape or its exact size. We were expecting it to be sort of round, because we always kind of envisaged these objects to be sort of round. And we got there, and it turned out to be like a rubber ducky. And I think this was it caught everyone's attention in the media quite a lot, because it literally looks like a rubber duck. It's got this head and this body. And I can't imagine how you figure out how to fly around that thing without bumping into it or whatever. But we started to get images back from this comet, and they mapped 100% of the surface of the comet, because they had to pick somewhere to put a lander down. Again, they built this lander 20 years previous, and they didn't know what they were going to be landing on. Do you call it candy floss here? The stuff you eat at the fair?
Cotton candy, thank you.
Cotton candy, okay, so we call it candy floss. So one of the scientists likened it to they didn't know if they were going to be landing on candy floss or cotton candy or cement. They had no idea if it was concrete hard or very soft, and they were going to sink in. So they had to build a lander.
You just have to build a spacecraft that's going to land on something that you don't know what it is.
We have no idea what it is.
20 years from now.
Exactly. It's easy.
Yeah, exactly. Trivial.
So they let the little lander go, and the lander is called Philae, and it just dropped to the comet. But again, remember, there's not much gravity, so the comet is not attracting that thing to it. The comet's still rotating in space, so they have chosen a landing spot, and they're like, yeah, we want to land exactly here. And sure enough, it did initially land exactly where they wanted it to go, on this object that's 3 by 5 kilometers in size, so it's not big, and it all hurtling towards the sun at the same time. Unfortunately, some stuff went wrong. One of the harpoons that was meant to fire when they landed in order to kind of hold it onto the surface and tether it there, they already knew when they were going through their procedures before they were going to release Philae that it wasn't working. So they already thought, okay, what can we do about this? There's nothing we can do. This, we have to just go for it now. We have to test it. So, they did their job right. They got exactly where they wanted to, but the little lander bounced, and it bounced about 1 kilometer up into the air. Now, the issue is that it could have just completely left the comet because it wasn't going to go back. It didn't bounce quite high enough that it left, so it went back down again, and it took a few hours, and then it landed again and had another bounce. So it's kind of hilarious. It did the kind of 3 landings in space, and they were only planning to do 1. Unfortunately, where it ended up was not the optimal position for the solar panels. So it was kind of under a slight cliff, but we then learned that comets have cliffs on them and, overhanging sections. It's kind of crazy. But it did run. It ran its primary science sequence when it got initially to the comet. So we actually ended up sampling some of the comet gases and some of the dust that was on from that initial landing site, and then did some further science later on. So we still learned an awful lot. So it kind of seems like a failure, but it wasn't a failure at all.
No, not at all.
It got a huge amount of science done. And we had, where I was working at Open University in the UK, we had one of the instruments on the lander. So we had a mass spectrometer that could measure some of the components from the gases in there. So we got to learn what was on the comet.
Right, and to your surprise, you got samples from like 3 places. I used to work with this guy, Ray Arvidsson, great guy, who would say all the time, there's no bad data. And so just because you didn't get the exact data that you planned to get doesn't mean you didn't get some great stuff. And you got the stuff from, because it was bouncing, you got it from like
we
several
actually got multiple
spots.
locations. And then we still have the orbiter that was, still orbiting around or flying around the comet at the time and doing its own work. It was measuring lots of other experiments and doing lots of other work and measuring dust coming off it and collecting that and looking at the plasma environment, how the comet reacts to the sun, which is very important because we don't really know how comets react to the sun. When we know that they get heated up and material comes off, but we found out that actually every time this comet 67P went via the sun, it loses about 1 meter of material off its surface. So it gets smaller and smaller because those volatile ices and everything get heated up and blown off the comet, and they take then that dust that is sitting above it, that's that kind of dehydrated layer on top, and it all comes off. So you lose a huge amount of material. So it's a very active environment. A comet is constantly changing. We go, oh yeah, they're these old objects and they preserve the very old history of our solar system, but actually if they come via the sun, they're changing all the time. And we see that they have seasons. We noticed that the comet had different seasons on it depending on where you were on the comet and where it was in relation to the sun. So and that moves material around the comet. We see movement of, like active processes like you would see on a planet. It's crazy.
Yeah, that's amazing. I hadn't heard that before. That's really cool. So long as we're talking about these space missions, I just want to give a quick shout out to the Dawn mission, which after 11 years of exploring the asteroids Vesta and Ceres is running out of maneuvering fuel kind of middle of next month, and so is going to say goodbye to us. But just a little shout out to Dawn for a long and honorable mission, increasing our understanding of the very objects that we're talking about here.
Yeah.
You were talking about we talked about this earlier, that there isn't necessarily a sharp distinction between these asteroids and comets, and so now that we've had these missions to kind of look at asteroids close up and look at comets close up, we're kind of learning more about how like there isn't asteroids and comets, there's more like kind of attractors in the space where there's things that we would confidently call asteroids and things that we would confidently call comets, but also a lot of things kind of in between.
Yeah.
So what have we learned from these missions that kind of helps us understand that continuum a little better?
So I think we've learned that, for me, I think what I've learned is that it almost doesn't matter. That, okay, so we have objects that sit at either end of this continuum. But if we want to study our solar system, it really doesn't matter which ones we study too much. And the ones in the middle are probably the most fascinating because they contain the primitive material. So the ones that contain a lot of carbon and a lot of organic matter. The ice is not, is important, but actually understanding the dust that came from the beginning of the solar system is great, and the organic matter. And so the next 2 missions that are going to study these objects are both going to asteroids. So we've got OSIRIS-REx, which is a NASA mission, and there's a Japanese mission called Hayabusa 2. They did Hayabusa 1 already, and that collected some sample and brought that back. And so it didn't go completely successfully, so they're taking another try and going to do it perfectly this time. But these 2 missions have arrived at their asteroids, and they're both basically primitive asteroids. So they're not cometary-like, they're still asteroids, but they have a lot of primitive material in, so we can try and understand these kind of beginnings of the solar system. So they're both going to be bringing samples back. I've forgotten right now what dates we're talking about, but it's kind of within 5 years, I think, something like that. We'll be returning materials. So they've started their mapping phase of these objects, and they're going to be looking where they're going to put their landers down and sampling. But it's proper science fiction stuff. I love it. It's just fascinating that they can do this. And,
we are going to the solar system and like going to visit comets and asteroids where they live and like bringing stuff back from there. Yeah, that's really amazing stuff. So we talked a little about how they're going to kill us all and what we would do about it. So we talked about kind of like spray painting in asteroids and things like that. One of the techniques I had not heard about before reading your book was gravity tugs, which is another interesting way of diverting asteroids or comets off their path. And it's nice because it works with unconsolidated things as well.
Yeah.
You want to explain how a gravity tug works?
So some of these objects, even the asteroids, like I said, the comets were not very well consolidated, not very well held together, because remember, this is the scoop of cloud kind of thing. And some of the asteroids, on the other hand, also are unconsolidated. They might be made of rocky material, but imagine just getting like a load of big pebbles and just kind of sticking them together, and they're sort of held there because there's a bit of gravity, and there's nothing really acting on them in space that would mean that they wouldn't just all fall apart, but they're sort of loosely bound together. These objects are particularly dangerous because they're hard to move. If you want to hit them with something, they're probably just going to break up. So we have to be very gentle with them. If we know one of these objects is heading towards us, it's hard to know how they're going to behave when they come through the atmosphere. So the gravity tractor thing is almost just taking a spacecraft up and using thrusters on one side to sort of gently nudge, and basically it's the attraction between that rubble pile and that spacecraft, which isn't very much, but if you've got enough advance warning, you start doing that little playing game and like nudging it back and forth early enough, then it will change its orbit. So essentially you kind of want to nudge it very gently. And it's just that gravitational attraction between the two objects, which obviously happens even if they're small. There is still something there. So that would be very useful if it were a rubble pile style asteroid. It could work with other ones, but I think that's probably the safest way to move one of those, maybe.
More research needed, right?
Yeah.
And that's something we haven't done before. We actually have fired a bullet, basically, Deep Space One, right? Fired a bullet into the side of a comet. Well, we haven't tried these other techniques at all.
So
it's all kind of theoretical at
There's
this
a
point.
mission called Deep Impact, which don't confuse it with the movie Deep Impact. And that was confusing my book, because my editor was like, oh, you've got a mission called Deep Impact, but there's also a Hollywood movie called Deep Impact. And I was like, yeah, that's complicated. So I think I ended up taking out all references to the movie.
Now they need to do a NASA mission called Armageddon.
Yes, that would be good.
Just to make things more confusing.
So yeah, this mission actually basically pushed a boulder, like fired a boulder into the side of this comet to see, well, basically to see what would happen, because it's fun, but also to excavate a hole so that we could see inside the comet. It was kind of went a little bit wrong, because they created so much dust from this, impact, that the spacecraft couldn't then see anything. There was just so much dust everywhere. But luckily, actually, the Stardust mission, when it carried on, when it had got its samples and sent those back, the Stardust next mission had carried on, and it was managed to image that hole in that crater that was created. So we got to see processes happening, and again, they saw changes happening over time in that crater that they created. So you see that we've got this kind of active comet thing again, which is really cool. So yes, it's kind of one space mission did it, and then we came back and had another look. So
So we're just about 40 minutes here, and probably about time to start kind of mixing in some audience questions while we're kind of finding the first victim and giving them the mic. Another major topic in your book was about mining asteroids and comets, so they actually contain material that would be useful to us on Earth. It's not just organics, but also nickel and platinum and things like that. You want to talk a little bit about kind of mining techniques and kind of what the state of the art there is?
So of course, again, it sounds like science fiction. It's like, do we really need to mine in space? But there's companies, a lot of them, a lot of stuff going on in California where we want to, there's actually companies investing in this, trying to think, right, can we go and mine these objects? We could mine the moon. There's lots of materials on the moon that would be useful, but equally, it might be easier to mine asteroids. They can be easier to get to. They don't have gravity, so they're easy to get back from if we want to launch a mission back. And they contain a lot of precious metals. So we all love our smartphones and everything, computers readers. Obviously, we're in Google. So we like all these materials that require precious metals. And if we're going to continue creating new technologies in the future, we need to know we've got a reliable source of things like palladium, platinum, all these things that are used in technology. We won't be able to develop new technologies if we don't know we've got a continued source of this stuff. And on Earth, things like platinum, well, it's expensive because there's not much of it. We find it very hard to mine. It's very dispersed throughout the crust of the Earth, and it's expensive to mine and often not very good for the environment to get out. If we go to an asteroid, well, there's tons of it. Actually, there's probably more platinum in some single asteroids than we've ever mined on the whole of the planet. So we run into economical issues if we were to mine it and bring it back to Earth. Well, we'd crash the market, and obviously then it will probably be not worth having done the whole mining thing.
Right.
Maybe we store it like we do with diamonds, and we release it gradually and control the market. Anyway, I'm not an economist, but there are issues to doing that. It may cost trillions of dollars, literally trillions of dollars, to actually launch these missions and go and mine these objects. But the chances you could actually, they could be worth way more than that. So there is, I guess, if you have a lot of money and you think it would be fun to go and mine asteroids, there is the potential you could make a lot of money. Of course, we need reusable rockets because it's just too expensive otherwise. We need to, so that obviously a lot of companies are working on that right now, being able to cheapen getting stuff into space because it's just massively expensive. But if we can find ways around this, and I think progress is definitely being made at the moment, we can get to space cheaply and we can start to mine these objects, but we don't have to bring all that stuff back to Earth. It could be useful in space, and we want to go to Mars, we want to venture out further into our solar system, but we need, first of all, fuel. It's very expensive to bring fuel from Earth. If we want to go out into the solar system, fine, we have enough fuel for a little while, but then if we want to land somewhere and go and visit somewhere else, we need fuel. And if we launch it from Earth, it's just very expensive. The more fuel you take, the more fuel you need to take that fuel. And there's an exponential relationship, and it just gets crazy. So if we can find the fuel in space, and sure enough, we have water, if we can split water and use get it into hydrogen and oxygen, we can create rocket fuel in space. So again, it sounds like science fiction, but we can then also use these objects to make materials in space, 3D print what we require. Instead of taking all our tools from Earth, which we currently do, if we go to the International Space Station, we have to take everything with us, and we have to launch missions just to, resupply it. Well, we wouldn't need to do that. We could just actually go and 3D print. So they're actually tested a 3D printer on the International Space Station.
Right.
And it sounds crazy, but yeah, that is something we could do. We just mine the asteroid, get the materials we need, and make the tools we require into space. So yeah, it's happening. It seems like, I think the first steps in asteroid mining are probably going to happen within the next few decades. The very tentative steps of like getting there, prospecting basically, seeing what these objects contain, and then figuring out what kind of missions we require to maybe tug them into an orbit where they're sort of safe and they're going to sit quite happily, so that we can then launch a mission to mine them in some way. Whether we need humans, it's unknown at the moment. This is why people talk about needing a moon base for a lunar base for humans to live, and that they could then mine from the moon kind of thing. So it's a lot of unknowns at the moment, but there's definitely progress being made. And there's like the US has created laws about mining in space and who owns the materials they've mined. So any US citizen, theoretically, if they mine something in space, they can own that stuff. Which is kind of crazy. And I don't know what the rest of the world thinks about this at the moment. I think Luxembourg are following very similar laws. I don't know if they've passed them yet, but again, Luxembourg is tiny. I don't know if you've been, but there's not many people that live there, so I'm not sure how many people are Luxembourg citizens. But yeah, is that fair? I kind of think, well, okay, I'm not a US citizen. I want to go and mine space, but I wouldn't be allowed at the moment to own the space that I mine. So yeah, a lot of issues and a lot of global issues, I think, that we need to
But it seems like they're worth working out because there's potentially so much wealth there, and it's not just wealth in terms of making you rich, but wealth in terms of, as you said, things like resources to make smartphones and stuff like that.
Exactly.
I'd never really thought about this before, but asteroids have all these resources that we need and a whole lot of fuel that we can use to help further explore the solar system. Asteroids are basically the convenience stores of outer space.
Yeah, I kind of said like they're the gas stations.
Right.
You just kind of pop there and get what you need and then carry on. Of course, it's not that simple, but yeah, I kind of like that idea.
Yeah.
Then it might happen in the future.
Right on. Okay, so I think we have an audience question ready to go.
Yeah, I was going to ask about asteroid mining, so...
Oh.
Okay.
Okay, good. I've ruined your question. I'm sorry, Bryant.
I actually have a question. Have you ever seen the movie Melancholia?
No.
Have you ever heard of it?
No.
You should check it out.
Okay.
Basically, the premise of that movie is that a large planet-sized body is heading towards Earth.
Okay.
About the size of Jupiter. It's huge.
Oh my goodness.
It's
okay.
huge.
Right.
Like just ginormous. But the whole thing is that the scientific community sees it well in advance, like several years in advance.
You would see that coming.
So they're planning it, and they're releasing all this information. I don't want to give away too much of the movie, but the premise is that it basically slingshots around the Earth, and they think it's going to pass, but the slight tug of gravity from the Earth is just enough where it reaches its apex that it turns around and comes straight back at Earth. So my question would be like, you're kind of doing the theoretical science around how we would deflect or move something that is smaller than Earth.
Yeah.
Is there any science or theoretical physics and science going on about how we would move something that could be much, much like magnitudes larger than the planet?
I think there's almost 0% chance of anything larger than the Earth hitting Earth, because the solar system has settled down now. So 4.5 billion years ago, Earth was hit by a Mars-sized body, we think, and that's what actually formed the moon. So it collided with the Earth. We're not sure of the details of that, whether it was a direct impact or a kind of a side shot, but it probably almost certainly vaporized the Earth. And then from that, we formed our Earth again, but also our moon. So that's the kind of thing that would happen. It would just be completely obliterated if anything larger than Mars were to hit us. But at this stage, the solar system settled, and I think it just couldn't happen. But you never know.
I'm sure it makes for a good movie. All the same. Have you seen this mic, by the way? This is really cool. You just toss it around.
I did wonder what it was when it was sat up here. I was like,
yeah, right.
So I was fascinated to hear about the inner and outer asteroid belt. And it sounds like they're materially different. The outer one has a bit more ice, which maybe you'd expect. It's farther from the sun. But other than that, are these different populations? And so what segregates them?
So it's just probably more based on density. So the inner objects are denser and formed under hotter conditions, so they're more consolidated, they're rocky, they're metally. The ones on the outer edge are probably formed where the comets formed and were knocked into there. So they are a lot less dense. They probably have a lot of pore space. So actually, when we got to the Rosetta comet, 67P, we were able to measure its density, which is really cool because although it's made of rock and it's made of ice, it actually has a really low density because it's got lots of holes in it. So they're not big holes, not like gaping big holes in the side of it, like cavities, but it's very porous at a very fine scale, but very porous, like it's got a lot of gaps in it. So it's just not very well pushed together. Whereas the objects on the inner asteroid belt are very probably no pore space whatsoever. So that basically controls it. So these, as you move on out, you've just probably got a transition gradually from the inner to outer.
Thank you.
Okay.
In college, I did something where we had designed these transmitters to put on near-Earth objects. That there was a lot of concern that the smaller objects that were harder to detect could be the thing that does us in, instead of the larger objects that are easier to detect.
Yeah.
And it was just a design class. We didn't actually deploy it, but is there any movement in trying to do anything to look at near-Earth objects?
So yeah, we are currently tracking basically all the near-Earth objects that we can possibly see. The ones that are sort of in normal orbits. I say those ones because there could be some random objects that are at the moment far out that are going to become near-Earth objects, but we don't know they're coming yet because they're very small. But so those are kind of the unknown unknowns, I guess. But the ones that we can see and we are tracing the orbits of all the time. So we're constantly updating where we think they're going and how they're spinning, because it's very important to understand how they heated up. I said earlier about deflecting them. If you paint one side a different color, it will spin differently. Well, there's two effects that happen in space, Yorp and Yarkovsky effect, and that determines how these things spin and how it affects their orbit, basically as they're heated up by the sun. So we sort of know most of them aren't going to hit us, but we need to just define those two phenomena very clearly, and then we can know exactly where they're going to go. So some of these objects are on sort of a hazardous list, but we just need to better define exactly where they're going, and then they can be removed from that list. But yeah, when we're talking about the size of these things, it's funny because even if it was just a couple 100 meters across, it could still cause a lot of damage, depending on what it was made of. If it's a pure piece of metal, well, yeah, sure enough, it's going to probably get through the atmosphere quite easily, and wherever that hits, okay, it might not cause global devastation like we saw with the dinosaurs being killed off. But, it could cause quite a lot of issues. And we've had impacts in the past which haven't been massive, but they can create things like, nuclear winters, essentially. You can have years and years, when you get a massive volcanic eruption, it's the same kind of thing. You can change the climate of the planet for a considerable time. And I would suggest that humans are fairly kind of vulnerable species. We want clean water. We require movement around the planet quite a lot. And I think if anything like that happened, we could be quite vulnerable species. So even if it was a smallish impact, it could just cause quite a lot of issues. But obviously the larger impacts, if we're talking kilometer-sized bodies or larger, they're going to be a bigger problem. So understanding those kind of small ones that are still quite large is a really important area, kind of 400 meters across, and so they're pretty dangerous and they're hard to see. So we need to understand those, especially if they're dark. If they're proper dark carbonaceous asteroids, they're very hard to see because they don't give off much light. So that's what astronomers rely on, these things giving off light. That's why comets are easier to see. They shine, whereas asteroids can be a bit sneaky. So we have to be careful.
I have a question about the interstellar dust that was collected. It might be outside the scope of this conversation, but I was wondering if it gives us any kind of understanding of the original Big Bang and maybe supporting the theory of the Big Bang, or is it really more like stuff that's 4.6 million years old and it's very localized dust?
So I'm going to have to say I don't know to some of that, actually, because I've not kept up with that interstellar stuff very well. But I know that it's basically allowing us to look into our local galaxy. And I don't exactly know when that dust was formed. But what they've been able to do is actually measure the isotopes of the elements of that material. And that allows us to understand a lot about our local environment, like what our solar system formed from. And obviously, we expect that different galaxies are going to be different compositions because they formed at different times. Maybe, we still don't really understand all of that. So, because we haven't been able to sample it or, look at it very clearly because these things are so far away. So it's kind of understanding a little bit further back in our history what is in there. But yeah, I'd have to say I'm not too sure.
So recently there was big news about this asteroid from outside the solar system that blitzed through.
Oh, I'm so glad you mentioned this. I hadn't mentioned it yet, so yeah.
Yeah, okay, great. Is that something that was a 1 in 100-year event, or was that a question of our sensors are getting better and we can expect to see more of them the more we look?
Exactly, the latter. So we think, so I'll just backtrack a little bit. So this object came through our solar system. We actually think now it was probably a comet, but we're not 100% sure. We weren't able to measure it very well because we didn't know it was coming. But so it was not on the normal orbit that all the other comets and asteroids and planets are on. It just literally came zipping through our solar system. It was so fast that it didn't even get caught into the gravity of our sun. It just zipped by. And it came from some other star system. We have no idea where. And it's probably been some interstellar traveler for forever. Who knows when it formed? It came from very far away, so it's been going for at least billions of years. And it just zipped through. So we don't know a lot about it. We just know that I think it's called Muamua. Is it called Muamua? I think it's Hawaiian for...
yeah, didn't know how to pronounce it.
Muamua, I think. And I think it's Hawaiian for something like distant traveler or something like this. Mm-hmm. I probably pronounced it wrong. I don't know Hawaiian. But basically, if we knew one of these was coming, we could launch a mission, again, to go and sample it, because this would be fascinating. We'd learn about that star system that it came from, which could be completely different to what we're seeing here, probably would be. It could be the same, who knows? But we know it came from somewhere else, and we just haven't seen one of these before. I think probably other objects like that have gone through the solar system, but we haven't spotted them. They go very fast. I think it was just chance that it was seen as well. But it is fascinating, and I would love to have some sample of that comet. It would be so cool to analyze. But yeah, I'm hoping, in the future, as we get better at seeing these things coming, again, it wasn't very big. It was also really weirdly shaped. It was like a cigar shape, really long, and kind of like, maybe it's some alien spaceship. Who knows?
So basically you're saying we're being visited by cigars and rubber ducks.
Yeah.
Groucho Marx would be so happy. So we just have a couple minutes left, and I wanted to ask you if European Space Agency or NASA or somebody came to you and said, hey, we'd like you to be the principal investigator, that is the top science person for the next space mission that's going to go and maybe explore one of these objects. What would you want it to be? What would you do with that mission?
Oh, I wouldn't be able to choose. I mean, so at the moment we've got these missions, Osiris Rex and Hayabusa.
Well, they're not giving you two missions.
Yeah, I know.
Just one.
So I would want to go and explore the Kuiper Belt better, get samples of it. I'd want to explore more of the comets, but equally, some of the really exciting scientific things happening right now are in Enceladus and Europa. Now, this isn't comets and asteroids, but this is potentially finding life in our solar system. These are moons of Jupiter and Saturn, and they have liquid oceans beneath their icy crust. And there's a really high potential that they could have life, probably not intelligent life, but there could be life there. And for me, at the moment, I'm just fascinated by that. And we are going to one. We're going to Europa, so hopefully.
My wife is working on Europa later.
Okay, so that's going to be soon, and we will hopefully go there. The Europa Clipper mission, Enceladus. Unfortunately, we found that Enceladus had this liquid ocean as well after they'd already planned this mission to Europa. But it might actually be a better place to look for life. It doesn't have quite the same horrible radiation environment that Europa has. So. I can't choose. I literally can't choose. Pluto is also fascinating. We've flown by it. We've learned a lot by just flying by it, but it's a Kuiper Belt object. It's basically a large comet, and but there's probably other really fascinating objects in the Kuiper Belt that we need to look at. So we just haven't explored it enough. And it's just too far away. So yeah, I need to kind of speed up time travel, and then come back and get some samples. But yeah. I don't know.
It's wonderful to have so many good choices. Right?
yeah, that's true.
Dr. Starkey, this has been a terrific conversation. Thank you so much.
Thank you for having me.
The book, absolutely, our pleasure. The book is Catching Stardust, Comets, Asteroids, and the Birth of the Solar System, and all the stuff we talked about and so much more is in it. I encourage you to read it. Please join me in thanking our guest today, Dr. Natalie Starkey.
Thank you.